Wow, a student found some car headlamps. Hopefully they weren't attached to a car, maybe on their physics teacher's desk or something. But they are labeled 12 volts, 55 watts. So that's its power rating. When it operates the most efficiently and best is at 12 volts and 55 watts of power. Part A, show the resistance of a single headlamp is 2.62 ohms. Alright, so it says show. It's not good enough to write R equals 2.62 ohms, right? Because we're given that. We need to show how they got that. So looking at your formula sheet, of course we have Ohm's law. Voltage equals current times resistance, where resistance would be voltage divided by current. And we're given the voltage, but we're not given current, we're given power. So how can we relate that to current? Again, in your formula sheet, we know that power is current times voltage. So current would be power divided by voltage. And with that, we could solve for the resistance. So solving for current first, 55 watts of power divided by 12 volts. That gives us 4.58 amps. And then taking that into Ohm's law, where we also have the voltage, resistance would be 12 volts divided by 4.58 amps, giving us our resistance of 2.62 ohms. So kind of went a roundabout way of doing this, right? We started with Ohm's law, realized, we're missing current. Then we used P equals IV to find current first, to then substitute it back into Ohm's law. Right, now this is, of course, an achieved question, because it's a show that, right? Show that the resistance is. I'll show you a much better way of solving this problem. I know, I should have started with it, but here we are. Now, this is not in your formula book, but I strongly recommend you ingrain this into your mind. Other forms of the equation for power. So we know power is current times voltage. It is also current squared times resistance. It is also voltage squared divided by resistance. Now, if you're wondering where these come from, you should definitely derive them yourself by using Ohm's law, like we just did before, and substituting it in for I, right? And then you'll get this power equation. Then try substituting it in for V, and you'll get this power equation. So it essentially combines the two steps that we did into one. And so now looking at the problem again, we are given voltage and power, and looking for resistance, we can use power equals voltage squared divided by resistance. So resistance equals voltage squared divided by power, or 12 squared divided by 55, which will again give 2.62 ohms. And that is a perfectly fine way of solving this problem. Alright, on to part B. So the student connects two of these headlamps, A and B, and another lamp, C, which is used to light up the number plate. And if you didn't know, you do need that number plate light to pass your run of fitness. How I know this is because someone crashed into the back of me and I had to get mine replaced. There you go. Anyway, we want to calculate the total resistance of this circuit. Before we even think about doing that, we are going to label each bulb with its resistance. So A and B are from the headlight before, right? So that has a resistance of 2.62 ohms each. There we go. Now, can we just add up all these resistances? No, right? We have a parallel component inside the series circuit. So for total resistance, I'll show you kind of a nice shorthand for writing your initial step. It is the resistance at C plus, now it's not plus the resistance at A and B, it's plus the resistance at A when it is in parallel with the resistance at B. Right? Because this branch, if we replace that with a single resistor, it would be in series with C, so then we would add them. But it's not a single resistor, it is two bulbs, so we need to combine them first. And so maybe let's do that on the side first. So RP for parallel, we know the equation is actually 1 over the parallel resistance is equal to the sum of the inverses. So 1 over 2.62 plus 1 over 2.62. And let's see what that gives us. So 1 divided by 2.62 equals, and we have 2 of them, so I'm just going to double that. And that is 1 over the parallel resistance. So to get the parallel resistance, we need to do 1 over this answer, which gives an equivalent resistance of 1.31 ohms. Cool, and that is that term there. So our resistance total is at C, which is 1.22, plus the combined parallel branch, which was 1.31, giving a total of, what's that, 2.53 ohms. And that would be merit if you got that far. Now I'll show you a simpler way of calculating the parallel resistance. So this is just an aside, very useful. Instead of using the 1 over sum, the parallel resistance is equal to the resistance of, like, the first branch times the resistance of the second branch divided by the sum of their resistances. So I remember it as the product, right, times divided by the sum of the resistances. And you can actually derive this equation from the one you know and love by rearranging for RP. So I encourage you to try get from that to that. Yeah, but again, you're welcome just to use this trick, that the parallel resistance is the product of the two resistors divided by their sum. And try it out, you'll get 1.31, and then of course we add that to 1.22 because that is in series with lamp C. The student now connects a radio with resistance R to the circuit. So they placed it in series with one of the headlights. Interesting choice. Now use physics principles, right, because we're doing a physics paper, to describe the effect of adding the radio that it would have on the brightness of lamp A. Okay, we can assume everything's operating, so current is flowing. Start by describing the effect on the circuit resistance. So just right off the bat, this is an excellence question. There are quite a few parts to it. There's current and voltage and how they're related through the resistance. So let's take it step by step. So let's go with what they suggest to describe the effect of the circuit resistance. So if we add this resistor, we are increasing this branch's resistance, right? If we combine that into a single resistor, it would have now a greater resistance than just bulb B, which means the parallel branch, that resistance would also increase, which means the total circuit resistance also increases, right? Because it's in series with bulb or lamp C. So that can be our first bullet point. So adding the radio, resistance R, increases total circuit resistance. Cool. Just a note here, if instead the radio was placed in parallel, it would actually reduce the overall circuit resistance because it's allowing for more pathways for current to flow. Hence, the parallel branch would have a lower resistance, so the overall circuit would also have a lower resistance. But in this case, it's placed in series in one of the branches, so the total circuit resistance increases. Okay, so what's that going to affect? Well, we know that the voltage supplied is constant, right? We're not changing the 12 volts. So we could say voltage is fixed at 12 volts. So what's going to happen? If we increase the resistance with a constant voltage, so voltage is constant. If we increase the resistance, current through the circuit will decrease, right? So by Ohm's law. So by Ohm's law, current decreases. And we should just specify here, that's the total current, or the circuit current. Okay, and so that's this current here. That's decreased, that's gone down. Now we need to reason about lamp A. So what's going to happen here? So I'll give you a few ways of thinking about it, because this is actually quite a complex problem. Firstly, if this current, the blue current that I've just drawn, has decreased, that means less of it is going to come to this junction, right? So you might think that less current goes to lamp A. Now, that is not the case, because this branch now has a larger resistance, so more of the current is going to want to go through A, and less of the current is going to want to go through R and B. So even though this overall circuit current has decreased, the current going through lamp A has actually decreased, or the current going through the radio and the lamp B has decreased. So we could use that argument, and then since current through the lamp has increased and its resistance is the same, its power, recall P equals I squared times resistance. Since current's gone up, for fixed resistance, power has also gone up. Yep, so that's one way of answering this. I'll give you another one, because I'm feeling generous, as always. So if the current has decreased, the circuit current, what can you tell me about the voltage across C? So voltage, current times resistance. Well, its resistance is the same. So if current drops, the voltage drops. Right, so now there's less voltage. I'll draw it in red. Less voltage across C. However, we know the total voltage must add up to 12. So across this parallel branch, there is more voltage, right? A greater voltage across the parallel branch, which of course means a greater voltage across A, which is what we're interested in. And we also know that power is V squared divided by resistance. So if the voltage increases, right, as it does across bulb A, for a fixed resistance, power also increases. So that's another way that you could argue that the power across or through bulb A has increased, so its brightness has therefore increased as well. So let's just put that into words. I'll go with the second argument. That is what is in the mark scheme, but the first one is just as valid. So where did we leave off? We left off with that the total current decreases. Now that means that the voltage across C also decreases. So V across C decreases, which then means the voltage across, so it's the parallel branch, or we could just say across A, because that's part of the parallel branch, increases. And the reason for that is by Kirchhoff's voltage law, KVL, which just says the voltage around the circuit must add up to, like in this case, 12, right, supplied by the battery. So we lost some across C, which means we need to add some across the parallel branch. Okay, now finally we can then describe how that relates to power. So P across A increases, and then the reason by P equals V squared over R, where R is constant and voltage increased, right, as in the above bullet point. Whew. And have we answered the question? Have effect on the brightness. I haven't used the word brightness yet. Final bullet point, therefore brightness of bulb or lamp A increases. Alright, that's a lot. So let's just recap this. We added this extra resistance, which then increased the circuit resistance overall, decreasing the current, which decreased the voltage across C, increasing the voltage across A, making it shine brighter. I strongly recommend you build this circuit in PhET. So if you haven't used PhET before, it's a educational website where you can do some simulations. Do the DC circuit builder. Build this circuit and adjust this resistance, like from 0 to infinity, and see what happens in terms of the brightness. Cool. And the final tip for this one, a way to think about a problem like this is taking the extremes. So instead of just a resistance, what if that had a resistance of infinity? Right? Sounds a bit odd, but bear with me. That means that this part of the circuit, this bottom branch, won't get any current. So all of the current flows through the top, which therefore means the brightness also increases. So that's just another strategy that you could use. Just take it to the limit, either infinite or 0, depending on the question. All right, I'm going to give myself another excellence because that's well deserved. All right, another excellence question. Give at least 3 reasons why the circuit would not be a good way to connect the 12-volt headlamps in a car. So a reminder, the student connected the radio in series with headlight B. So what could go wrong? Well, what if your headlight stopped working? No current can now flow through that bottom branch, and so even though the radio still might work, since the circuit is broken, that pathway, the radio won't turn on. So that's pretty useless. What else? What if lamp C broke? So lamp C, the one at the bottom there. If lamp C broke, well, again, no current would flow into the entire circuit, let alone just the radio. No current would flow to either headlamp. So that's also useless. And what else? What if you turned the radio off? but you wanted the headlight be on. Well, too bad, because since your radio's off, no current is going to flow through, and so your headlight won't work, forcing you to listen to the radio whenever you want the headlight on. So there's 3 examples, and then the final one is, scrolling up a bit, the headlamp was rated for 12 volts, and if you notice this circuit, 12 volts is supplied, but there'll be some lost across this bulb, leaving less than 12 volts across the headlights. So that's also not very effective. So really, they should have connected everything in parallel in this circuit. So let's put that into a few bullet points. So if C stops working, current can't flow, which then of course means everything stops working. Right, and then what if B stops working? Well, no, what was it? The radio, excuse me. If the radio stops or is off, current can't flow through that branch, meaning B, headlight B stops working. And then what else? So that C bulb blowing, radio must be on. And then what did we say about the 12 volts? So 12 volts is not supplied to either headlamp, as some voltage goes across C. Cool, and there's 3 reasons why that circuit is trash. So don't build circuits like that, guys. Alright, see you next time.